Okay, so the second kind of situation that we are going to talk about, and we're going to look at what sort of forces we have restoring the system to equilibrium, is when we have a vertical mass spring system. So obviously this is going to look a little bit different. We've got a spring with let's say we just have a spring hanging from the ceiling. This is a fixed ceiling, it's not moving anywhere. Well, we're going to end up with some sort of an equilibrium point that the spring naturally stretches to. If then we take the same spring and we attach a mass to the end of it, well, obviously, we're going to end up with a spring that has been stretched to a different point. And so really this here is going to be a new equilibrium point. Because once we've added this mass there, it's going to basically stay there. And that's the definition of an equilibrium point, is where it sort of naturally comes to. And in this case, if this spring has been stretched a little bit, well, it's going to be the force that is pulling it back up is going to be balanced by the force of gravity pulling it back down. So we can figure out where this new equilibrium point is by kind of just drawing a little free body diagram here. I'll just draw it on the side. So obviously we've got the force of gravity pulling us down. We've got a force from the spring pulling it back up. And anytime we're in equilibrium, that means we aren't changing. So really, if you have a vertical spring system, then the force of the spring is going to be equal to the force of gravity at equilibrium. If you were to then stretch the spring even further, well, then the situation starts to look a lot like a horizontal one, where we have a force that is restoring it to the new equilibrium. So the big difference between horizontal and vertical is that the equilibrium position can sometimes change when we're talking about a vertical system, depending on how much mass we add. So let's take a quick look at this as an example here as well. I'm running through this fairly quickly, but I know these videos can be a little bit hard to watch if they're too long. But so when a 2.45 kilogram mass is hung vertically from a spring, the spring stretches by 12.4 centimeters. Okay, and there's a couple questions that we are answering here. First one, what is my springs constant? And then second one, well, we'll get to the second. We'll start with just this one. What is my spring constant? So let's draw a couple pictures here just to make sure we fully understand the situation. Okay, so at first we have a spring that's just hanging there. Then we take that same spring and we add this mass onto it. And this mass is 2.45 kilograms there. And so this spring has now been stretched an additional 12.4 centimeters. And so we want to know what strength of spring, what stiffness of spring is going to cause the mass and the spring to stretch this distance. So, of course, let's write down everything we know. We know the mass is 2.45 kilograms. And we know that the spring stretches by 12.4 centimeters. So remember, that's X. Anytime we're talking about a stretch, really we're talking about X in our formulas. 12.4 centimeters is 0.124 meters. Okay, so that's all we know. Like we did just above here, free body diagram, well, we've got the force of gravity and the force of the spring are going to balance each other out. If we want, we can write our net force equation here, where force net is equal to mass times acceleration. At this new equilibrium point, acceleration is going to be 0. So really this works out to be force of the spring minus the force of gravity is equal to 0. Remember, we can replace spring force with K times X. Again, we've already sort of accounted for the sign. The sign is pointing up because it's restoring, so we don't need to put the minus sign there. Minus mass times acceleration of gravity is equal to 0. So really all we have to do here is solve for K mass times gravity divided by the length that it has stretched, 2.45 kilograms, multiplied by 9.81 meters per second squared, divided by 0.124 meters, and we find that our K value here, our stiffness, is 194 newtons per meter. So if we had a spring that had stretched further, well, our K value would be smaller. If we had a K value that was bigger, then the spring would stretch less. So hopefully that makes sense. Really, it's just a simple sort of free body diagram situation. It's just that we have a new force that we're talking about here. We're talking about the spring force. If we had a second part to this question, let's say we add, if we add another, what was the mass here? 2.45 kilogram mass. How much further will it stretch? And we can take advantage of the fact that we know that the force and the amount that it stretches are proportional to each other. So since a 2.45 kilogram mass here caused a stretch of 12.4 centimeters, that means for every additional 2.45 kilogram mass that we add, it's going to stretch another 12.4 centimeters. So we don't even have to do any calculation to answer this question here if we understand that displacement and force are proportional. We could have drawn another free body diagram. Our force of gravity would be bigger, our mass would have doubled, and we could solve for x. But that's not necessary, since we can just sort of think about it and realize that it's going to stretch the same amount.